Okay, so here we are, 2 laws down, we got 1 more to go. So we need Newton's third law. Now, there's a bunch of stuff. The first law, most people at least think they've got down pretty well. But when you stop and pay close attention to it, it's actually a little more complex and doesn't necessarily agree with what people would think, but it is still actually the case. Newton's second law is one that people who are familiar with it, many times they don't fully understand that equation, and that gets them into trouble trying to apply it. So there are little things that we can learn here and there depending on how good your understanding of Newton's laws of motion is. And that brings us to Newton's third law of motion, which is one of the ones that people tend to know kind of the best. So here we go. Newton's third law of motion. This one is not an equation. Basically, only the second law is the one that's an equation. So I like to give the definitions of these to get across the ideas that they talk about. Now, Newton's third law is the one that you hear from a bunch of different sources. It's applied all over the place in literature and fiction, all these different things, day-to-day talking. So it's the one that usually is listed as for every action, there is an equal and opposite reaction. That is kind of the summarized version of basically the textbook definition for Newton's third law of motion. And so this is one that is covered in quite a few physics classes, physical science classes. This is one that you may have heard all the way back to, I think, middle school for me. I think I remember studying Newton's laws of motion in middle school, and the second law never stuck out to me from that far back because you weren't really doing a whole bunch of rigorous mathematics, and so, of course, the one that's actually an equation is the one that kind of falls out of viewpoint. But Newton's third law, a bunch of people have an understanding of Newton's third law, so let's talk about that. For every action, there is an equal and opposite reaction. Let's go back to something that I introduced earlier. Action. What does that word mean? Well, it's a reference to what we would call a force, a push or a pull. And we end up with a reaction. You could call that a reacting force, but it's just another force. They're both forces. Actions and reactions are forces that are working together or against each other, I guess I should say more accurately. Okay, so here we go. Let's take a look at this. The common one for people to take a look at, we're going to talk about some forces and take a look at a real-life example of it. So I've got a textbook here, and we're going to hold it like this. Okay, let's analyze the forces acting on it. Now, one of the things that it's got is the force of gravity. We're near the surface of the Earth, so Earth's gravity is pulling down on the textbook. Okay? So, according to Newton's third law, for every action, if there is a force, there must be an equal and opposite reacting force. So, we've got the force of gravity pulling down on the book. What is the reacting force, the Newton's third law pair, that is predicted by Newton's third law? Okay, well, what other forces do we have? We've got a physical force of me holding the book. When I ask this to a classroom, which this classroom is empty, so I'm mostly talking to myself, but when I ask this to an actual classroom, the common response that I get is, well, the Newton's third law pair, the reacting force, is me holding the book up. And so that's usually what most people's understanding is. I found that that is by far the most common understanding. We have gravity down, and we have my physical contact force, a normal force, up, and they are equal and opposite. And that is what most people use to explain Newton's third law. However, there's a problem. And it's exemplified with what I just did, dropping the book. I do this in class, and a lot of people don't like it because it's the dropping the book day, and it's scary. That being said, here's the thing. Gravity is pulling down on the book. And people say that the Newton's third law pair is the physical contact force from my hand holding it up. But it's not. And I can demonstrate it to you, because Newton's third law doesn't say, most of the time if there's an action, there'll be an equal and opposite reaction, but not if the reaction has already put in its appropriate 40 hours that week, because we can't afford overtime. And also not on soft holidays because, well, the reaction force has a union, and the union doesn't allow that to happen. No. Newton's third law says for every action, for every force, there is an equal and opposite reacting force. There's always a pair. Now the problem with that is, if I'm holding the book, gravity is pulling down on the book, and I am supplying a force upward. Now many people think that this is the action-reaction pair, but here's the problem. If I take my hand away, as I did just a moment ago, one of these forces is gone. And Newton's third law doesn't say, most of the time, if there's an action, there's going to be a reaction. No, it says for every action, there is an equal and opposite reaction. So if one of these forces goes away, the other must go away too. Which means, if they are actually predicted by Newton's third law, gravity pulling down and my hand lifting up, if I remove my hand, gravity must forget this book exists. I won't drop the book again. You can rewind and be shocked again as no, gravity did not forget about the book. The most common understanding that people have is demonstrably wrong. For every action, there is an equal and opposite reaction. Here's the problem. Most people get caught up on this part, the equal and opposite. They think that that's the important part. It is true when I'm holding the book like this, that the force of gravity is downward, and the normal force, the physical contact force that I apply to it, is equal and opposite. But not in accordance with Newton's third law. Newton's third law isn't equal and opposite is the most important part about this. In fact, pardon me, that's a side aspect of it. The most important part of this is, for every time there is a force, if you push or pull on something, there is always a reacting force. Forces are shared. I'm going to write that down in just a minute because that's my definition for Newton's third law. In fact, you're going to find that I don't even include equal and opposite in my definition of it because it's such a loaded statement. When you're working in physics, you are going to find that there are thousands of forces that happen to be equal and opposite, not because of Newton's third law. They are not an action-reaction pair, but they are equal and opposite in accordance with Newton's second law. The forces are balanced, so the thing is sitting still. It is not changing its motion, or I should say it remains sitting still, or it remains moving at a constant velocity. So let's talk about this just for a moment. There are a few things to unpack here. First thing I'm going to do, I'm not just going to pull the rug out from under you and say, okay, thanks, bye. I'm going to fill this in so that you have a proper understanding of the forces we were looking at. Let's start with my physical contact force, me holding the book. Now, some people may think that the reacting force is the force of gravity, or that we've got the force of gravity in my hand is the reacting force, but that's not actually it. Here's what I want you to think of. So I'm holding the book. I want you to imagine that you close your eyes and you hold out your hand with the palm upright, just right in front of you, and I would come over and I would at some point put the book on your hand. Would you know when I put the book on your hand? Why? Well, you'd know it's there because it pushes down on your hand. As soon as the book is there, it pushes down on my hand, and my hand pushes up just the same. So to hold the book up, the book must push down on my hand. That is the Newton's third law pair. The book is pushing down on my hand, and my hand is pushing up on the book. And if I were to take my hand away, I am no longer pushing up on the book, and the book is no longer pushing down on my hand. The same instant, I cannot push on the book without it at the same time pushing on my hand. And if I do not push on the book, then it does not push on my hand. That is the Newton's third law pair. Now, the important thing that is overlooked in Newton's third law is, by its very nature, the one force is on one object, me pushing on the book, and the reacting force is on the other object, the book pushing on my hand. This is what Newton's third law is actually about. It's not equal and opposite. That's part of it, but that's not the important thing. The important thing is these forces and reacting forces are talking about an interaction between two objects. A great example I like to give is a high five. So I want to give you a high five. You hold your hand up, and my goal is to hit your hand. Great. I hit your hand, giving you the high five. But what happens to my hand? it gets hit. How do we know? Well, my hand stops. In fact, if I do the following, high five, too slow. I do not hit your hand, and what happens to mine? It continues moving because it doesn't have a force applied to it, at least until it gets to the end of my arm, and then there's a force that will bring it to a stop. But for me to hit your hand must hit me back. I apply a force this way, your hand will push just as hard back that way. Equal and opposite. One force is on your hand, and the reacting force is on my hand. And they are tied together. I cannot hit your hand without my hand getting hit, and vice versa. In fact, the idea of action and reaction implies that one of them is secondary to the other, but that's actually not a good understanding. A good understanding is they're both actions. They're both forces. They both happen at the same time, because what Newton's third law is actually telling you is that what we understand to be forces is an interaction between two objects. And it is between those two objects. It affects both of those objects. We can view it as a force acting on one of them and an equal and opposite force acting on another, but fundamentally what Newton's third law is about is that forces are shared between two objects, and always two. You can have several interactions going on where you can have forces that go between many different objects, but we break them down where one object is interacting with another and then possibly interacting with another over here and another over here. There can be a whole bunch of interactions, but the key thing about this is when you have a single force, it is always an interaction between two objects. Forces are shared between two objects. This is what Newton's third law is about. And these forces manifest themselves as one of them one way and the other being the other way, and they will be equal effect on each of the objects, or not effect, but equal force as we understand. I should be careful with that, because you may end up with things having a different result based on their masses. But the key idea behind Newton's third law is this, that what we understand to be a force is actually an interaction that is being shared between two objects, and they are both affected by it. You cannot have an instance with our current understanding of physics in which you apply a force onto something without, at the exact same time, it applying that force back. I cannot hit your hand without your hand hitting mine. I cannot hold this book up without the book pushing down on my hand. Those are the action-reaction. And when one of them is removed, the other is gone at the same instant. This is the proper understanding of Newton's third law of motion. Commonly misunderstood. And even more so, one of the reasons why is it is commonly mistaught. If you were taught that the proper application of Newton's third law is that gravity down, normal force up, and that's Newton's third law, you were taught wrong. You were taught demonstrably wrong. I could drop the book again, but I think we got our point across. This is Newton's third law. This is what is the fundamental reality, and it matches everything that you see. Anytime one force is applied on an object, you have an equal and opposite reacting force. On the first object, you've got two objects, one here and one here. In fact, I've set up a couple of rules that help you identify the Newton's third law pair. Rule number one, same type of force. Now, there are different types of forces. In my class, we go through and we introduce them in a bit of a list right after we do this. There's a gravitational force. That's one type of force, so gravity. We've also got a physical contact force. We call those normal forces. There's a frictional force. There are tensions, so ropes and string. There's, air resistance, drag, a force of drag, slowing things down. There's a bunch of forces, electrostatic forces, magnetic forces, at least the way that we treat them in introductory physics. The key to understanding Newton's third law is to realize that they must be the same type of force. Why? Because Newton's third law is talking about one interaction, one force that is being shared between two objects. So it must be the same type of force. And rule number two, this also ties with what I gave you. It must be between the same two objects. Newtons. If you apply these two ideas, you will find the Newton's third law pair. So for instance, I apply a physical contact force up on the book. The book and my hand are the two objects, and I am applying a physical contact force up on the book. So by Newton's third law, same two objects, it's got to be the book and my hand, and the same type of force. We already covered the physical contact force of my hand holding the book up, so the only other thing it could be is the physical contact force of the book pushing my hand down. My hand can feel the presence of the book, and if I don't tighten my muscles a bit more, then it will go down because my hand will be pushed down. Great. There's one last thing that we need to take a look at if you still want to watch. This is all the information that you would need, but there's one thing that I've left dangling out in the air, both literally and figuratively. I explained the Newton's third law pair to the physical contact force, my hand on the book and the book on my hand, but I never addressed the original one, which is the force of gravity. Well, it is a force predicted by, and thus, by Newton's third law, there must be an equal and opposite reacting force. So let's think about this. Okay, we're asking about, well, here's the book, and it has a force applied onto it, a force of gravity. I'm going to call that F sub little g. And it's applied downward. Okay? According to Newton's third law, there must be an equal and opposite reacting force. Okay, well, let's apply my rules to see if we can figure it out. First off, it's got to be the same type of force, so we're looking for a force of gravity. Okay? Now, we also need to have it between the same two objects. Well, I know one of the objects, that's the book, and it's being pulled down by the gravity of what? The Earth. The Earth is the cause of the gravity around here, not the scale. But here's the Earth. Well, according to Newton's third law, if the two objects are the book and the Earth, and we've got a force of gravity down on the book, then Newton's third law says that there's an equal and opposite reacting force that is a gravitational force, so it's going to be equal, and opposite, so it's going to be up, a force of gravity up. According to Newton's third law, this must be what we're dealing with. But that seems weird, because I'm now telling you that while the book falls down towards the Earth falls up towards the book. And as crazy as that sounds, that's exactly what happens. But let's take a look at that, because you're probably thinking, okay, he's gone off of his rocker at this point. Where's the comment section? Where's caps lock? Caps lock is needed for this. Bear with me. Let's get some experience applying Newton's laws of motion here. Newton's second law in particular. Let's take a look at the book. So we're going to have a thought experiment here where we can ignore all the other things on Earth and the sun and all of that. We're just going to take a universe that is comprised of our book and of the Earth. Okay, so I've been using this book in class. I had a balance around here earlier, and this has a mass of 2.6 kilograms. So we're going to say that we're going to first off look at the book. So the book has a mass of 2.6 kilograms. I put it on a scale and managed to get that it was 2.6 kilograms. Great. I also did some stuff where I made a measurement of the force of gravity using a spring scale, and I found that the force of gravity on the book was equal to 25.5 newtons, or pretty close to that. At least reading off of my spring scale. Do I still have it? Yeah. I've got a spring scale here that goes up to 50 newtons. I had to rig up a thing to actually hold it there, but it came down to about 25 and a half, at least to the best of my ability to read this. Great. So this is me collecting actual numbers. All right. Now, if I look at the point where I take my hand away and we let go of the book, and we're looking at the force of gravity acting on it, I'll draw a free body diagram, which we introduced in my class. But I'm jumping a little ahead. There's my book, and I'm going to draw all the forces acting on it. Well, the only force acting on it, if I've taken my hand away, is the force of gravity. Great, and we made a measurement of that. That's 25.5 newtons. Okay, so if this is my only force, then I can apply Newton's second law. My sum of forces is equal to my mass times my acceleration. In this case, we're looking specifically in the y direction. Well, my only force acting on it is the force of gravity, and I'm going to put a negative sign, because remember, Force is a vector, and I usually make down the negative direction. So the force of gravity is directed downward, so I'm going to put a negative. Equals my mass times my acceleration. In this case, it'll be my acceleration in the y direction, because nothing's happening in the x. Great. I can fill some things in. I know that the force of gravity was 25.5 kilograms from my measurement, equals a mass of 2.6 kilograms times the acceleration in the y. I divide both sides. I'm going to divide this by 2.6 kilograms. Divide this by 2.6 kilograms. And oops, I apologize. I miswrote that. That is not 25.5 kilograms. That is 25.5 newtons. Bad Sanchez. Yep, newtons. Get your mind straight, man. Head in the game. There we go. Calculator. Great. 25.5 negative, technically, divided by 2.6. I get about blue. A sub y, my vector, my acceleration in the y, is negative 9.808 meters per second squared, because a newton divided by kilogram will leave me with meters per second squared. Oh. Negative 9.81 meters per second squared. So that's my acceleration. The book, because of the force acting on it, has an acceleration of 9.81 meters per second squared. It falls down and falls down pretty quickly. Give me just a moment, I'm going to check on my recorder. Okay, great. Sometimes my phone acts weird, so I want to make certain that I wasn't standing here talking to myself the entire time. Here we go. So we just took a look at the book. We found by taking actual measurements, I put this on a balance, a scale, regular, one of the scales that we have here in class, and it told me that it was about 2.6 kilograms. And then I took a measurement of the force of gravity on it. I had to set up something a little more complex than this, but I was able to find that the force was about 25.5 newtons. Maybe I should have just rounded that to 26 newtons. And we found that the acceleration due to gravity was right at about 10 meters per second squared. Negative 9.81 is what we got with the measurements here, which is pretty close to the accepted value. That is the accepted value, actually, but neither here nor there. Now, we've got the other part. All of that looks great, but it's this part that most people think that I'm a raving lunatic who should not be teaching physics and instead should be relegated to living in a dumpster outside of like a Target or something, talking about the end of the world. This is the part that is crazy for most people. I've said that when we drop the book, because of Newton's third law, the force of gravity from the Earth is pulling the book down, and by Newton's third law, there must be an equal and opposite force of gravity pulling the Earth up. When I drop this book, the book falls down towards the Earth, and the Earth falls up towards the book, which most people would think that, okay, just back away, let him keep talking, and everything will be fine. We'll escape from here. Let's draw our free body diagram of the Earth. Now, we said that there's a force of gravity from the book, because Newton's third law says that any force will be shared between two objects. So if the Earth is pulling on the book with gravity, the book must also be pulling on the Earth with gravity, which, as strange as that sounds, is true. Everything in the universe that has mass actually generates some gravity. Now, it turns out that when you look at the equation, which we'll do later in the year, the gravity generated by me as an object, or the book as an object, is a really small amount. And we either need incredibly long time spans or something else in order to actually see any legitimate motion. The only gravity that we really pay attention to is from really big stuff, like the Earth, or the sun, or the moon. So, most small objects, like a book, or me, or you, we do actually generate gravity, but it's a real small amount of gravity. Now, when you study Newton's law of gravitation, the big equation that we use for gravity, you'll find that both objects actually have their masses go in there. So the book and the Earth have their masses go in to find the force of gravity. But we're using the simpler approach here, and we're going to apply Newton's third law. Now, Newton's third law, and this is the important part, remember how I said that Newton's laws sound silly sometimes, unless you're paying extra close attention. If you didn't watch the part where I talked about Aristotle, Aristotle's description of natural tendency of motion makes a lot more sense than Isaac Newton's, if you're not paying close attention. Aristotle said that things will always slow down and come to a stop, which is what I see on a regular basis. Isaac Newton says things will always continue moving in a straight line at a constant speed forever, and that's not what I see here, unless I realize that I got to take into account that there's friction and air resistance, forces acting on that object that result in it slowing down and stopping. Newton is right, but you have to pay a lot more attention, and sometimes you have to look real close. Newton's third law is also correct. Even though right now this looks weird, we have to look much closer. There is a force of gravity from the book on the Earth. And if we're ignoring everything else, there's a lot of other stuff happening too, but just in regards between the book and the Earth, we have this. Now, Newton's third law says that the forces are equal and opposite. Now, that's important to note because most people think I'm crazy when I say that the book falls towards the Earth and the Earth falls up towards the book. They think that they're both going to do the same moving. They're not. Newton's third law doesn't say that the objects will then do the same moving. Newton's third law says they're subject to the same magnitude of force in opposite directions. So while the Earth pulls down on the book with 25.5 newtons, something that I can easily measure, by Newton's third law, the book must also pull on the Earth with 25.5 newtons, much harder for me to measure. But by Newton's third law, this is the prediction. They must be equal, they are, and opposite. This one is up, the force on the Earth is up, and the force on the book is down, at least from our frame of reference. Now, let's ignore all the other things that are acting on the Earth. There's a bunch of them, it turns out. But let's go ahead and apply Newton's second law on the Earth as though it were only interacting with the book. Well, we've got a force of gravity upward, force of gravity plus a positive, because it's up, equals the mass of our object times the acceleration of our object, in this case in the y. Great. We know that our our force, I keep doing that, is 25.5 newtons. And we're going to set that equal to the mass of the Earth, 5.94 times 10 to the 24th, I think. Might be 5.97. I should double check that. Kilograms. Anyway, it's about 6 times 10 to the 24th kilograms. Feel free to put a message in the comments about how I should have been better prepared. Going off of memory here. It's either 5.94 or 5.97, I'm pretty certain. But I do know it's times 10 to the 24th. We could round this to one significant figure and make it just 6, and we're still pretty close. Regardless, acceleration of the y. Now, many of you may be asking, how do we know the mass of the Earth? Well, that's a fascinating story, too. And I mentioned it a couple times that I'm going to try and make some additional videos on Kepler's laws of planetary motion, which is somewhat related to this. And I can give you an answer to that, to this, where we get this number from, with Kepler's laws of planetary motion. When you understand the physics well enough, you can get numbers that seem like they would be impossible to get. You just have to get real creative. And that's the joy of science. All right. According to Newton's second law, Newton's third law says that if the book is being pulled on by the Earth with 25.5 newtons, that the Earth must also be pulled on by the book of 25.5 newtons. And by Newton's second law, if that is the net force being applied to the Earth, ignoring all the other things for our purposes, then that should be equal to the mass times the acceleration of the Earth. So when I do this, I get, let's see, 5.94 times 10 raised to the 24th. And I'm going to do 25.5 divided by answer. My acceleration in the y is a positive, so upward, 4.29 times 10 to the negative 24th meters per second squared. Okay, what that means is that 0 point, and then there are 23 zeros. And then finally you end up with a 4.3. All right, so this is a profoundly tiny number, which is why this is what's actually happening. The Earth does fall up, but let's see how far it goes. If this is the acceleration, well, that could get complex to see how far it goes in the time it takes the book to fall. The book only takes about a second or so, or maybe less, depending on what height you drop it from, to actually fall. Let's check something out here, just for the sake of interest. Let's say that the Earth would move maybe the thickness of a human hair, which I would put at somewhere about maybe 100 micrometers, which is equal to, what would that be, 1 times 10 to the negative 4th meters. It's about a tenth of a millimeter. So we could probably do a measurement of the thickness of a human hair. At least in general, we probably could. Anything smaller than that, we might need some special equipment. We might be able to measure that. Don't know. We could get some calipers or something. But let's find out with this acceleration that we've got, how long it would take the Earth to move the thickness of a human hair. So for that, we would use, let's assume a constant acceleration. We've got delta x equals v naught times time plus 1/2 at squared. So here's our kinematic equations like we used in class. Let's say that the Earth starts off not moving, at least with respect to the book. So let's go with delta x. We want our delta x to be 1 times 10 to the negative 4th meters. Great. And then we've got an acceleration of, we said, 4.3 times 10 to the negative 24th meters per second squared. I've got 3 pieces of information I can solve for my time, so plugging things in, I'm going to get, let's see, delta x is 1 times 10 to the negative 4th meters equals our initial velocity, which is 0 times time, that's just going to be 0. Let's see, plus 1/2 our acceleration, 4.3 times 10 to the negative 24th times t squared. Okay, so here's what I'm going to do. I'm going to take 1 times 10 raised to the negative 4th, that's this. I'm going to multiply it by 2 to get rid of the 1/2, multiply it by 2. Then I'm going to divide it by 4.3 times 10 raised to the negative 24th. Great. And so I get the following. 4.65 times 10 to the positive 19th equals t squared. I multiplied by 2 to get the 1/2 over there, and then I divided by 4.3 times 10 to the negative 24th. If you get a very tiny number, double check how you're putting it into the calculator. Remember, we're dividing by this whole quantity. You probably divided by 4.3 and then multiplied by 10 to the negative 24th. You should get a big number. Now I need to take the square root of that, and we find that I end up with, I could have used scientific notation, 6.82 times 369, times 10 to the 9th equals our time. Great. So the time it would take with this acceleration for the Earth to move the thickness of a human hair, fall upward by the thickness of a human hair, is, let's see, divided by 3,600, because this is in seconds. Don't forget your units. This is seconds squared. Seconds, okay, so I divide that by 3,600. That gives me 1.89 times 10 to the 6th hours, so that's almost 2 million hours, divided by 24 hours in a day. That is 78,900 roughly days. Sorry, did I do that right? Yes. And then divided by 365, that is 216 years. Great. So, I have told you that while the book falls down towards the Earth falls up towards the book, and that is actually true. It's just because of the mass of the Earth, the acceleration is so low that the Earth doesn't do any discernible movement. Now, just because we can't see it doesn't mean that it doesn't happen. It's so small that we would have a hard time, even with our current ability, to actually measure that. Now, how can I say with confidence that the Earth actually does that? Because every time we test Newton's laws of motion in any way that we can measure, it does work out that way. Now, I'm open-minded to the fact that this might be wrong. Maybe this is me talking about our New Age Aristotle's laws of motion, and they match everything that we see to the detail that we're looking at, and that's the best that we can operate on. That's what science is. It's not a bunch of facts and this and that. It's what we can put together to understand the universe around us. And so long as it matches with what we see, or at least can see, then it's a perfectly valid one. If it doesn't match, then we must get rid of it and find something that does match. And that's the important part about science. It turns out that what Isaac Newton laid out has been updated multiple times. It's not necessarily wrong, but as we got to more and more complexity, we found that we had to update it for certain circumstances. But this is what will get you through the vast majority of your interactions, particularly in introductory physics, and even up to probably even the graduate level. This is a proper understanding of Newton's laws of motion, and that results in an understanding of dynamics, why things move.